All right, let's take a look at some example problems. So here we have a bicycle pedal. So there's a gear here. We've got a foot that's applying a force. So it gives us some information. It tells us that the length of a bicycle pedal arm is 0.152 meters. So that is referring to this distance here. So that's going to be our 0.152 meters. And then it says that a downward force of 111 newtons is applied by the foot when at the angle shown. So the force is going to apply here straight down. So that's going to be our force. Oh, I guess I should have drawn the arrow here because this is our lever arm R. Because that is going to be our lever arm. I guess we don't know that technically yet, but we do by finishing reading. And it wants us to know what is the magnitude and direction of the torque exerted by the foot about the axle of the bicycle gear. So that's how I know my lever arm is going to be the same as this 0.152 meters, because that is going to be the distance from the axis of rotation to the point where the force is applied. So the axis of rotation here is actually through the center, so that way the bicycle pedal can either rotate this way or that way. Now, without even having to do the right hand rule, you could probably look at this and figure out that this is going to cause a rotation in this direction. Now that is the clockwise direction. So our final torque should come out negative, but it's not going to come out negative on its own. So we're going to have to make sure to add that negative or indicate the direction of the torque, okay, once the magnitude and the direction of the torque in our answers. So we have to know where the axis of rotation is. We have to know where the force is applied to find R. So then, now that we have everything labeled, we need to make sure that we've drawn an extended body diagram, which we have. We need to make sure that there aren't any other forces that could be causing torques. Technically, gravity could be acting and causing a torque, but we're going to neglect gravity for now because we don't actually want to find the net torque. We want to find the torque exerted by the foot. But if there was going to be some other torque due to gravity, we might have to consider that and draw that on as well. So making sure to read the question and answer only what is being found is important. Plus, we don't have enough information to figure out what the torque due to gravity is, if there is any. So with this, our equation, torque, is going to be RF perpendicular. That's the method that I usually use, because I generally find it easier to keep the lever arm intact and find the component of the force that is perpendicular to the lever arm. So what we would need to do is figure out what component of the force would be. So they're defining this angle right here, theta, to be 60 degrees. So that is the 60 degrees related to this angle right here. But is that the theta that we need to do sine theta? Well, we need to make sure that if we're going to use RF sine theta, in order to do that, sine theta has to be the angle between R and F. So is that theta the angle between R and F? No, because it doesn't, that angle does not intersect the force, okay? So that means this is not the correct angle for that. So I would need to find the component of the force that's perpendicular or find the correct angle theta. Well, doing that essentially does the same for both. So this is a right triangle though that I made right here. So if this is 60 degrees, then this angle right here is 30 degrees. And if I were to resolve that force into components, one of which is perpendicular, so I could actually resolve this, and this component right here would be F perpendicular. And F perpendicular is going to be the opposite side of this triangle. So if I draw that kind of out over here. So here's my force. Here would be F parallel to R. Here would be F perpendicular to R. So that's just the same triangle. This is 30 degrees. So you can see that F perpendicular is going to equal F sine of 30 degrees. 30 degrees is also an angle between R and F. So it meets both definitions. So that means our torque is going to be RF sine of 30 degrees. So in this case, this was an example where the angle that they gave you was not the same angle you needed to plug in, which is why you have to stop and think about it first. Don't just plug in the angles they give you. So when we plug in for R, that's going to be 0.152 meters. We plug in for F, that's going to be 111 newtons, sine of 30 degrees, and you plug that into your calculator. You should get something like 8.4. So we've got 3 sig figs in the problem, so 8.44 Newton meters. So our unit is Newton meters. Now this gives us the magnitude, but it wants to also know the direction. The direction of the torque, if we want to do the shortcut, that would be just curling my fingers in that clockwise direction. So that's going to be into the page. Okay, so that would be the direction of that torque. The other way I could have figured that is by putting my fingers in the direction of R, rotating my palm in the direction of F, then my thumb points into the page once I curl my fingers. So either of those two methods works. So this would be a negative torque, but the better direction is into the page. All right, so there's that first example. All right, so what we have is we have another example problem. This time we have multiple forces acting. We want to determine the magnitude of the net torque and the direction of rotation. And we're going to do that relative to the fulcrum being the axis of rotation. So I didn't write out all the words on this one because it would take up too much space. So I just kind of got the picture here. So we have some information. We have a block that is at rest. So we can assume that there's friction or something holding this in place, so it's not sliding down. That would be, ooh, that'd be a fun problem if it was actually sliding down, because that would mean that its torque would change over time. That's kind of fun, but we won't have to deal with that. So we can just assume that it's stationary at that location, being held in place by friction. We can assume that with this fulcrum that it has only one point of contact, and that point of contact is serving as the axis of rotation. We can assume that that axis of rotation is essentially through the page, right here, so that way this thing can rotate in the plane of the page. We have a hand here that is not drawn, that is applying a downward force, kind of pulling this thing down. Think kind of like this is like a mechanical advantage. I'm trying to lift the box. And then there's actually a board that this is resting on, and this board has mass. Sometimes this is kind of like a seesaw problem. Sometimes when you see seesaw problems, the board has a negligible mass compared to the people. But in this case, the mass of this board is non-negligible because the block is 5 kilograms and 1 kilogram for the mass of the board is significant. So that means there is a gravitational force that is acting on the board. And since we're looking for the net torque about this axis of rotation, we have to consider all of the forces that are acting. So we have to, this is kind of leading us into our next topic, which is rotational equilibrium. But in this case, we don't know whether this is balanced or not. It doesn't look very balanced. It looks like there's going to be a net torque. So we have actually 3 different things that are happening. Basically, we have a gravitational force that would act straight down. That would be m times g here. So that would be the force of gravity. Now, technically, the force of gravity is not the proper way to identify this force, because that is acting on the box itself, not necessarily on the board, okay, on the axis, which is this axis of rotation. But we can, it's fine if we identify that. Technically, there's a normal force acting because the gravitational force is causing a normal force on the board. But it's going to have a value of that force is going to be m times g. So I'm going to use a big capital M because this is the bigger mass. So I'm going to use a big M times g for this. We have numbers, so we'll plug them in at the end. So the other thing that we have is we have this force of the hand. Its force is already labeled. So then there's a gravitational force. So where is the gravitational force going to act on this board? Well, technically, the gravitational force is acting everywhere along the board. Because the board is composed of a whole bunch of different masses, and the Earth is acting on all of those masses. But what's really cool is if you were to calculate the torques due to all of the different masses, the net torque actually adds up to be the same as if you treated all of the mass as if it exerted at the center. So when you have an extended body object with mass and you need to find the location where the force is applied in order to do lever arm stuff, we always assume that gravitational forces are acting at the center of mass. So this is going to be the force of gravity, little mg, for the board. And we're assuming that it is acting at the center of mass. So it's acting at this 0.50 meter mark. Now, if it was non-uniform, that center of mass could be anywhere. But in this case, because it is uniform, we are assuming that it is acting at that midpoint. So that's important for whenever we're looking at extended body objects. Now, what we did is we treated this block here actually as a point mass. Because compared to the length of the board, it's not very significant. So we just assumed it was at the center. But I did that here automatically. So we're just assuming that that is acting at the center of mass, but we're treating it more as a point mass than we are anything else. So it works kind of either way. So the next thing we need to do whenever we're looking at these problems is we need to identify the lever arms for each of these forces. Well, I'm going to identify this force is force 1, this one is going to be force 2, and this one over here is going to be force 3. So I need to identify each of those lever arms. So if I was to draw R1, it would start here, and it would go towards where that force is being applied. So that's going to be R1. R2 is going to be from the fulcrum over here. And then R3 is going to be for the fulcrum all the way down here. Now, R1 is given. R1 is going to be the 0.250 meters. But we don't know right off the bat what R2 and R3 is. We can calculate them. I can see here that since this force is being applied at the midpoint, and they identify this distance as 0.25, well, then if I do 0.5 minus 0.25, that means that R2 is going to be 0.250 meters as well. So in this case, I didn't draw this very well to scale, but those are actually the same values of lever arms. And if I look at R3, it's going to be the total length of the board, which is 1 meter, minus that 0.25. So R3 is going to be 0.75. That was too many. 0.75 meters. So now we have all of those lever arms. We need to figure out which ones are causing positive and negative torques. So if I look over here at force 1, if I put my fingers in the direction of R, rotate my palm in the direction of the force, curl my fingers, that one's up. So that one's going to cause a positive torque, because that is going in out of the page, which is causing a counterclockwise rotation. If I do this one here, I actually have to get up from where I'm sitting and kind of move around. So I put my fingers in the direction of R, rotate my palm in the direction of that force. That one's going to be into the page, and I can see that would cause a negative torque. And this one's in the same direction at the same side of the axis of rotation, so that one's also going to cause a negative torque. So even though all three of these forces are pointing downward on the board, they are actually causing different torques because the torque depends on the direction relative to that axis. So the other thing I'm going to have to worry about is that none of these forces are at 90 degrees to the lever arms. So what I need to have to do is figure out kind of where that angle comes into play. So they've identified this 20-degree angle for us right here. But that is not the angle between R and F for any of those. But if I wanted to figure that out, it's pretty easy if I look here, because that 20 degrees makes a 90-degree angle right here with this force. So that means this whole angle right here, that is going to be 20 plus 90, which is 110 degrees. And that 110 degrees is the angle between R and F, actually for all of these right here. So those ones right here. So that will give us the 110 degrees. That's not the same angle here. Well, it is, but it's on this opposite side. So if you extend R1 out, then this is also 110 degrees. So that will work. So we can use 110 degrees for our angle for all of those. So then what I need to do is, now that I've identified, so I've done some steps, so let's kind of review those steps. I've identified all forces. So I essentially made an extended body diagram. So by making an extended body diagram, I have made sure that the forces are drawn essentially starting on the object and pointing away. So in this case, the board is kind of what we were interested in. So they start on the board and pointing away. That wasn't too hard to do in this case. I've identified all the lever arms. For each of the force. For each force. We have identified the angles. Or you can find F perpendicular or R perpendicular, depending on what you want to do. So basically, so that we can use the torque formula. We have identified the direction of rotation. And the sign of the torque for each of the forces. Okay, so we have done all of those steps already. So the next thing we need to do is we need to write a net torque equation. So my net torque is going to be my torque clockwise, because those are positive, or counterclockwise, sorry. My torque counterclockwise minus my torque clockwise. So I'm going to use magnitudes for these so that I only have to account for the negative once. So my torque clockwise is going to be torque 1, because that's the only one that's positive. And then I'm going to subtract essentially torque 2 and torque 3. So I'm going to write it like this. I'm going to give each of those a negative because each of those are negative here. Okay, and then torque 1, torque 2, and torque 3, tau 1, tau 2, tau 3, those are magnitudes. So I've already accounted for the directions and the signs there. So torque 1 is going to be R1, F1 sine of theta. These all have the same theta in this case, which was nice. It's sometimes the angles will be different depending on the type problem you're working. So you'd have to make sure you found each of those angles, but in this case they're the same. So then that's going to be minus torque 2, which is going to be R2, F2 sine theta, minus torque 3, which is going to be R3, F3 sine theta. So in this case, I can actually factor out that sine theta to simplify this down. So R1, F1 minus R2, F2 minus R3, F3 all times sine theta. So we're going through this non-numerically because you should always go through it non-numerically first, plus a lot of problems you work will be non-numerical. There will not be numbers to plug in, so if you're used to plugging in and simplifying, you're cheating yourself every time you solve a problem. Plus, these are showing the steps that we are actually applying the physics. So it's really important to go through these steps when you're actually working your problems. And then I can plug in numbers. So R1 is going to be 0.250 meters. F1 is going to be M1, the big M times G, so that's going to be 5.00 kilograms times 9.8 meters per second squared. Minus R2 is also 0.25 meters. I only did 2 decimal places because this only had 2 decimal places, so even though this one had 3 with sig figs of the proper number of decimal places. And then F2 is going to be this mass, so that's going to be 1.00 kilograms times G, which is 9.8 meters per second squared. And then I'm going to have to subtract R3. R3 is going to be just be the 0.75 meters times F hand, which is 10.0 newtons. And then all of that gets multiplied by sine of 110 degrees. So if we plug that in, gives me 2.16 Newton meters. Now that came out positive. Really? Well, interesting. So that actually came out positive. So what that means is that, that actually this positive torque is larger. So that means that this is actually has a 2.16 Newton meter torque, and that is actually giving us a counterclockwise rotation. Cool, I wasn't expecting that. So even though there were more torques, more forces acting in the clockwise direction, this guy's actually larger. This is causing this box actually to be lowered rather than lifting it up.